Welcome to The Explainer. Today, we're jumping into the story of one of chemistry's most versatile and maybe misunderstood families of molecules. So let's just dive right in with a question. Think about this for a second. What single thing could possibly connect the fuel in a car, the scent in a bottle of perfume, and the antiseptic in a first aid kit? I mean, they seem like they're from completely different worlds, right? Well, the answer, it turns out, is just one word: alcohols. Yep, they're the invisible thread tying all of these incredibly different things together. So in this explainer, we're going to follow the entire life story of an alcohol. First, we'll ask, what are they, really? Then, we'll take a trip to the chemical factory to see how they're born. After that, we'll check out what they do out in the world, their life's work. And finally, we'll become detectives and learn how to identify them by their unique chemical fingerprints. All right, first things first. What actually makes an alcohol an alcohol? Let's get down to the basic building blocks. So, at its heart, any alcohol is an organic compound that has at least one very special feature: a hydroxy group. You'll see it written as -OH. That little combo of an oxygen and a hydrogen atom is the superstar of the molecule. It's the functional group that defines what an alcohol is and gives it all its unique powers. But, not all alcohols are the same. We can actually sort them into three main categories, kind of like family members. You've got your primary alcohols, where the carbon holding the OH group is only attached to one other carbon. Then there are secondary alcohols, where that carbon is attached to two others. And tertiary, you guessed it, that carbon is connected to three other carbons. And trust me, this simple difference in structure changes everything about how they behave, as we're about to see. So, now that we know who they are, let's go behind the scenes. Welcome to the alcohol factory. Let's see how they're actually made. Whoa, okay, look at all these different ways. It turns out there are a ton of different recipes for making alcohols. You can see you can start with all sorts of different ingredients, alkenes, halogenoalkanes, you name it, and use different conditions to end up with an alcohol. It just goes to show you how important they are in the world of organic chemistry. Let's just zoom in on one of these methods for a second: reduction. So you can take an aldehyde and reduce it to get a primary alcohol, or take a ketone to get a secondary one. But here's the cool part. It's about picking the right tool for the job. For aldehydes and ketones, a gentler reducing agent like sodium borohydride works just fine. But if you want to reduce a really stable carboxylic acid, you have to bring out the big guns, the much more powerful lithium aluminum hydride. Then there's another method that's just so beautifully simple. It's called nucleophilic substitution. All you do is take a halogenyl alkane, that's a carbon chain with something like a bromine atom on it, and heat it up with some aqueous sodium hydroxide. The little OH group just comes in and swaps places with the halogen, and voila, you've just made an alcohol. Okay, so we know what they are, we know how to make them. Now for the really exciting part. What can they actually do? Let's check out the life's work of an alcohol. And the answer is, well, a ton of stuff. They can burn completely. That's combustion, which releases a bunch of energy. That's why we use ethanol as a biofuel. They can also react with carboxylic acids to create esters. And esters, they're the amazing molecules that give things like pineapples and pears their delicious, fruity smells. They can even do the reverse of how they were made, undergoing substitution to become halogenoalkanes again. But out of all the things an alcohol can do, there is one reaction that is the most telling, the one that truly reveals its character. And that reaction is oxidation. And this is where that whole primary, secondary, tertiary thing we talked about comes roaring back. This is a huge deal. Primary and secondary alcohols, they can be oxidized. But tertiary alcohols? Nope, they are completely resistant to it. And that difference is the key to everything. Let's look at primary alcohols. Think of their oxidation like a two-step journey. If you oxidize it gently and you distill the product out as soon as it's made, you can stop the journey at step 1 and get an aldehyde. But if you hit it with a stronger oxidizer and heat it more intensely under reflux, you force it to go all the way to the final destination, a carboxylic acid. It all comes down to the conditions you use. Okay, so what about our secondary alcohols? Well, they're a little different. They can be oxidized, sure, but it's a one-way street with only one stop. They oxidize to form a ketone, and that's it. The journey ends there. They can't be oxidized any further, which is a really clear difference from their primary cousins. So, we've just figured out that different types of alcohols react differently when you try to oxidize them. which, is super useful information. It leads us perfectly into our final section. How do we use these differences, like chemical fingerprints, to tell them apart? This is where the science gets really practical. How do we take everything we just learned about oxidation and turn it into a simple visual test that lets us see with our own two eyes exactly what kind of alcohol we're dealing with? Well, the answer is a beautiful, satisfying color change. We use a special oxidizing agent called acetified potassium dichromate 6, and all you really need to know is that before it reacts, this stuff is a bright, vibrant orange. And here it is, the big reveal. It's so cool. If you add this orange solution to a primary or a secondary alcohol and warm it up, a reaction happens. The alcohol gets oxidized and the orange dichromate ions get turned into green chromium ions. You see a clear, undeniable color change from orange to green. And with a tertiary alcohol, you guessed it, absolutely nothing happens. The solution just stays orange. It's a perfect visual way to tell them apart. But what if you need to be even more specific? Well, for that, we've got another trick up our sleeve, the iodoform test. Now, this one doesn't work on all alcohols. It's a very specific test for a very specific structure, an alcohol that has a methyl group right next to the carbon with the OH group. If it has that exact structure, you'll see a pale yellow solid form. It's a super precise identification tool. And hey, before we wrap this up, here's a fun little fact that might surprise you. We tend to think of these chemicals as pretty reactive, right? But believe it or not, alcohols are actually weaker acids than just plain old water. It's true. Those carbon chains attached to the oxygen actually make it a little less likely to give up its proton. All right, let's pull it all together. The story of alcohols is pretty awesome. It all starts with that all-important OH group and their classification as primary, secondary, or tertiary. We learned they can be made in all sorts of ways and can do everything from powering cars to making things smell nice. And, most importantly, the way they react to oxidation gives us a fantastic visual test to figure out which is which. Which kind of brings us full circle. So, are alcohols just simple little molecules? Or are they something more, like one of chemistry's ultimate multi-tools, shaping the world around us in ways we never even notice? After hearing their story, I think the answer is pretty clear. Thanks for joining me.